Okay. Talk about max min. At the critical point, got max min of a function of two variables. At a critical point, which is where fx and fy are both zero. I'm not going to write that out. I think everybody knows what a critical point is by this point, by this time of the course. If not, you really have some review to do. And please do it. Okay, anyhow, let's just take an example. If fx is greater than zero, fy is less than zero at a critical point, then we have a saddle point. Why? Because the function is concave up in the, let's say this is the origin. It doesn't have to be the origin, whatever the critical point is. If the critical point happens to be at the origin, it'll look like this. In the xz plane, you got a curve that's concave up. In the YZ plane, you got a curve that's concave down. It's like you're walking along, you've just hit a low spot, and now you're going to go back uphill. But if you go to the right or left, you're going to go downhill. So you'll have this shape. That's a saddle point. And you can think of the way a saddle is constructed. In front of you, the saddle is like this, so you don't slide forward or backward. In this direction, it's like this because your legs got to go somewhere, okay? Then in this case, we don't have a maximum or minimum at the critical point. Now, if fx and fy are both greater than zero, you could still have a saddle point, okay? Because, okay, yeah, it's fine. You're here, it's like this. If you go forward, it's like this. If you go this way, if you go that way, it goes down, okay? And in that case, again, you have a saddle point, curves downward at the 45-degree angle. It doesn't have to be at the 45-degree angle. If there's some angle, some direction you can go in where you go downhill both ways, but if you turn, turn to the right angle, you go uphill both ways. That's a saddle point. Okay, so if fx and fy are both greater than zero, doesn't ensure a saddle point. And fxy becomes important. So if fxy okay. If fxy doesn't mess things up, then you have a minimum. Similarly, if fx is less than zero, fy is less than zero, and fxy doesn't mess things up, then you have a minimum. So what you end up wanting to look at is fx times fy, which has to be positive. Okay, if fx and fy are, if the product fy is negative, that means one of them is positive, the other is negative, and you have the saddle point. Okay. So this would be an example of that. And then you look at this minus the square of fxy. Okay. Now I'm not going to go through the whole thing, but that's what you've got to look at, and that should prompt you to what you have to review if you don't understand it. It's fairly simple. Okay. Okay, we want to look at Lagrange multiplier. Now there's a formula for Lagrange multipliers. I'm not interested in talking about the formula, it's pretty easy to use. People have very little trouble using it. However, what's the idea? Because we need to understand the geometry so we can actually use these things, think of them when we need them, don't have to rely on memorized formulas, rely rather on images. You know, we don't absolutely need to do that, but that's one of the things I'm going to be testing. Okay, Lagrange multiplier. So we got f of x, y, z. We want to maximize subject to g of x, y. And I'm going to just do a function, two variables, three variables, x very much the same. Function subject to a function g of x, y equals a constant. Some constant. Okay, what's this mean? First of all, g of x, y equals a constant in the x, y plane. G of x, y is defined everywhere, but if it's equal to constant, that will generally give you a curve in the x, y plane, not necessarily a function. This thing could go back on itself, it could do about anything. Okay. Now, as an example, if g of x, y is let's just say x squared plus y squared, and y equals the square root of the constant minus x squared. It could be plus or minus, and that gives you a circle. Of course, we know this gives you a circle, x squared plus y squared equals r squared. It's a circle of radius equal to the square root of the constant. The point is, if you have some formula equal to a constant, corresponding to g of x, y equals a constant, you can solve it for y in terms of x, and that gives you a curve. Okay, so g of x, y equals constant. Okay, well, at any point on this curve, the gradient of g of x, y is the direction of maximum increase. Okay. Because your direction along the curve is, let's just say here, and along this curve, g is constant. So the direction of maximum increase is perpendicular to that. Probably a little hard to read that. It's the direction of maximum increase perpendicular to the direction along the curve. And that's the direction of the gradient. So if this is your direction along the curve, this is the gradient del G. Okay. Now you're going to reach your point of maximum value of f of x, y when the gradient of f of x, y aligns with the gradient of g. In other words, when the gradient of f of x, y is in the same direction as g, or the exactly opposite direction, depending whether you're doing a maximize or a minimize. That means if you're moving in this direction, f of xy isn't changing. Okay, so it's maximized if the gradient of f is parallel to the gradient of g. Okay, again, g is constant along this curve. So in the direction tangent to the curve, g isn't changing, meaning the direction of maximum increase of g is perpendicular to that direction. You want to maximize f of xy. That's going to occur when the gradient of f of xy is perpendicular to the curve, because if the gradient of f of xy is not perpendicular to the curve, it's this way or this way, that means that as you move along the curve, you're either increasing or decreasing. Okay, so f of xy is maximum or a minimum, talking here in terms of maximum, but it could be a minimum if del f is parallel to del g. So the condition is equal to some constant. Del f is a multiple of del g. We generally use symbol lambda to indicate this. Okay, well, del f is a vector with an I component and a j component, so is del g. So the equation del f equals lambda times del g is in fact two equations. The I component of del f has to be lambda times the I component of del g, and the j component of del f has to be lambda times the j component of del g. Same lambda. So there are two simultaneous equations here, and the equation g equals constant. That gives you three simultaneous equations, okay? And those three simultaneous equations can be solved for x, y, and lambda. This is actually three equations, because this is actually two equations, one for the I, one for the j component. Okay. In higher dimensions, well, if this is in three dimensions, then this equation would be three equations, one for the I, one for the j, one for the k. Okay, well, it goes on like that. You can have two constraints in three dimensions and a lot of things, but here's the basic geometry of it, which is all I'm going to really talk about, as what underlies the mechanical procedure. Okay. Now, I wish I had an audience here. It's more motivating, so I'm a little flat right now, but I'm going to move on. Okay. That's about all I want to say. Yes, okay. All I want to say about this. Okay, integrals. Okay, if you have a function z equals f of xy, you could integrate. I guess I'll talk about what the integral means first. Okay, so here you have x, y, z. And let's just say you have some region down here in the XY plane. Let's just make it a rectangular region for right now. So you have y equal to some constant here, y equal to some constant here, x equal to constant here, x equal to a constant here. Then above this rectangle in the XY plane, you have some surface. And we can sort of represent that surface. I don't really need dotted lines. Let's just say that the surface looks something like this up here. I'll shade a few contour lines. Okay, so we've got some surface up here. We can visualize the integral of the function f on this rectangular region. I could give this region a name. We could call it D, but I'm not going to get into the notation. I want to talk about the concept. And of course, you work through the details. But the integral of f on the region, and we should understand, and nobody ever does, very few people ever do. We should understand that an integral is just an average value times the measure of the region. Now, by measure of the region, in functions of a single variable, the integral of f from a to b is just equal to the average value of f times the distance from a to b, not displacement, because an integral could be negative. But in 2 dimensions, it's going to be the average value of f times the area of the region. I'm not saying everything, it's the average value of f on the region times the area of the region. Okay, if the region's small enough, the average value of f is pretty close to any old value of f. So the average value would be close to any chosen value. Okay, well, the way I've sketched this, it looks like you probably got a 20% variation in the value of f between, let's say, here and here. Okay, this distance and this distance. Different, or let's say this distance and this distance, and maybe it's more like 30 or 40%. Okay, so this region's a little too big to say that we get a good idea of the integral on that region. Okay, so we take a small region. We take a delta x by delta y increment, where we implicitly assume delta x and delta y to be very small. If this region is small enough, then there's not room for this f of xy to vary much. So if we come up to the function, it's going to have some slope, but not much. And the region that we get here is pretty close to a rectangle. The values at the corners don't vary by much. If the region's small enough and the function is nicely enough behaved, meaning it's continuously differentiable, then smudge my delta x, delta y, and delta x by delta y. Oh, where's my pi? Okay, delta x by delta y increment here. This becomes nearly a prism, and the average value of F is close to any value. Okay. Average value of F times area well, the contribution of this little area increment, let's say within this region that we're talking about. Okay, I'm not going to try to draw that, to draw in color. Maybe to draw in color real quickly. So we got this small region here. It projects up to some region here. And the average value of the height from here up to here is pretty much the same anywhere. I can say if X star, Y star is within the increment, then the contribution is going to be close to F of X star, Y star, delta Y. Okay, now that's not exactly how it's been explained, but that's what we mean by the integral. The integral is the sum of F of X star, Y star, delta X, delta Y. Mod all increments in the partition of our region. So there's our region. This is just one increment in the partition. And the region partition is a bunch of little increments. Okay. So the integral of F with respect to area over the region is approximately equal to the sum of your F of X star, Y star, delta X, delta Y. Now, in practice, we partition the region by first partitioning either the X or the Y integral. Okay, X over here. So that the X equals 4. this interval here between these two horizontals is the y-axis. Not sure that's clear there, should be clear. This is the way we've done those. Okay. The partition of this region would be let's say your x interval runs from x equals a x equals b. So this line here is your line x equals a. This line here is your line x equals b. Okay. This whole line x equals a. So the run out from x equals b and x equals b. So your partition would be a equals x naught less than x1 less than so forth less than xi minus 1 less than xi less than etc. up to less than x equals b. Partition is your x. Now, if these lines here are y equals c and y equals d, and you would have c equals y naught plus yj minus 1. Less and y. Then the of f with respect to arrow would be the sum of the sum of yj. I'm not gonna write out build x line, build yj. I build x line is just x line minus 1 minus x I minus x I minus 1 delta yj is just the width of this interval yj minus yj minus 1. And this approaches the interval from a to b because the x interval has been partitioned from a to b of the interval from c to d of f of x y dy dx. And this can be seen for a given I, you can see that y has been partitioned. So if we look at our region here, between x equals a and x equals b, and between y equals c and y equals d, we partition our x's first. And Might have to stop this. Because that music is playing. Interrupt my concentration here. Maybe. I do respond to music. You can always hope that this doesn't inspire me to start dancing, because if I start dancing and you see it, you'll never be able to look at anything again. Okay, so anyway, let's say your X goes in this direction. Yeah, I have it right. I did that before the music started. Okay. Well, when you partition X, you get strips like this. So the typical partition, this is your typical partition. This is your xi minus 1 and your xi. Then you think of partitioning. So you have a typical y over here. Now, you've now divided your region up into this square, little rectangle. And here you would have your y plus yj minus 1 on this line, y plus yj along the right line on this line. So we can kind of maybe indicate this. So this little increment large is the increment xi minus 1 less than or equal to x less than or equal to xi. And then less than or equal, we kind of do like this. We're not going to get into that. You got your yj minus 1 less than or equal to y less than yj. And then here you have your annual point xi star yj star. So that corresponds to what I said over here in a tiny region. The point at which you choose to contribute to evaluate this average value of function is going to give you something close to the average value of the function. In other words, the function at this point is going to have a value that's very close, if the region is small enough, to the average value of the function over the region. So we can say that at a small region, f of x, y, yj, f of xi star, yj star is near the average value of x on this region. And waving my hands a little bit, I'm not going to do the official limit definition. I'm going to leave that to you. As delta x and delta y approach 0, your delta xi, delta yj approach 0. this is going to approach the average value on this region in the limit in a way, a specific way that ensures that as you take your limits, again, assuming again that f is a well-behaved function, you get the accurate expression for the integral over the entire region. Okay. Now that's a little different than the way I've explained it in class. Because I start with the idea of average value here, but I really want to emphasize the idea of average value. This can be made rigorous. Okay, at least on rectangular region. This justifies these sums because, again, for any given I, you got your xi interval, and then you got yj intervals within this strip. If you add all the contributions of these y subintervals within this interval, you get, come on, okay, there we go. Okay. The total integral that you get within this strip oh, that's right. Okay. This approaches the integral within the delta xi strip. And then if we sum that up over all the i's from 1 to n, because this is just integral over one strip for x sub I, we get the integral over all strips. Then we take a limit. Then this expression approaches, well, whatever did it. Okay, we get this integral, and if you have f of xy, then it's not too difficult to integrate. You can do these integrals, and everybody knows how to do these integrals at this point of the course. Okay, well, that's the idea, and that's the reason for more complicated regions that we describe our regions in inequalities. So I'm currently out of space here, and I don't have a good place to write anything, so I've got to rearrange the board. So pick up in a second, and we'll just pause. Okay, actually, due to time constraints, I've got a class coming in. I'm going to have to stop here. We'll pick this up a little bit later. What I've tried to illustrate here with the integrals is simply the concept of the integral. The details that we've been through, the details are very similar to the details that are implicit here. We'll go on with setting up integrals over regions and in various coordinate systems in a separate video.